Hello, ladies and gentlemen. Welcome back to chemistry, and also welcome to your first ever edition of video notes. So today we're going to be looking at solutions and solubility, but particularly about the concentrations of them. And in your warm-up, I asked you to look at what a good concentrated solution was and what a good diluted solution was. And my guess is that some of you, for concentrated solutions, you mentioned things like lemonade or hot chocolate. And for dilute solutions, you might have mentioned some medicines are better when they're diluted rather than too concentrated, especially if you're giving it to a really young child. Or some acids and bases are better when they're dilute because they make better cleaning agents that way. So I'd like you to look at these two solutions. Solution A is really concentrated and solution B is really dilute. And I want you to tell me the differences you see between these two things. And I want you to look not only at the macroscopic, what's in the beakers themselves, but also at the microscopic, which is depicted in these circles. Remember when we're talking about these things that solute is usually a solid or a gas, and that's what gets dissolved in the solvent, which is usually the liquid. So at this point, go ahead and make some observations while you pause the video. Some things that you might have noticed is that there's less liquid in this beaker and much more in this beaker. You also might have noticed that this liquid is a darker color than this one. I've had some debates about whether it's purple or blue, but either way, this one's darker. If we look microscopically, we can see that there's more solute in this circle than there is in this one. There's a lot more solvent particles, which are the red ones. Note that if I counted, I might actually find more solute particles in this beaker because it's taking up more space, but there's more solute per solvent in this case. That's really important, that solute per solvent. So here we have our true definition of the concentration of a solution, and like I said on the previous slide, it's how much solute is dissolved per solvent in a given quality of solvent. That's the really important part here. So when we look at solutions, we can either call them dilute, which is a small amount of solute per solvent. We also sometimes call this a weak solution. We also have concentrated solutions, which are a large amount of solute. Again, that's per solvent. And sometimes we call these strong solutions. So go ahead and pause the video here to get all of this written down. When we talk about concentration of a solution, we can express it mathematically three different ways. The first way is percentages. Now, when we talk about percentages, it has to be all mass or all volume. You can't do mass over volume or volume over mass. It has to be one or the other. When we look at percentages, remember it's solute per total solution. That's what ST stands for, solute, and SLN is solution. So take a second and pause here to write down percentages. The second way that we can talk mathematically about concentration is parts per million, which we abbreviate ppm. Now, ppm is a really common way to talk about the concentration of pollution in the ocean because we typically use it to measure really small concentrations. And the way I think about parts per million is I imagine a box of Legos, and this box has to have exactly 1 million Lego pieces in it, and they all need to be the same size and the same shape, but they need to be different colors. So when I have this box of Legos that's all the same size and all the same shape but different colors, I can talk about how many parts per million of a given color that I have. So for example, I could say if I have 700 red Legos in my box, that I have 700 red parts per million of Legos. Okay. So when we're talking about the ocean, that part could be a gram or a milliliter. We can make that part whatever we want, but we're saying that I have so many parts out of a million parts of whatever I'm measuring. So go ahead and pause and take a second and write down parts per million. The third way that we have mathematically to measure concentration is molarity. And it's important that we use the capital M to represent molarity because lowercase m is molality, and that's a different measurement that we are not getting into. We are sticking to molarity. So when we're talking about molarity, we have moles per liter. And it's important that we remember that our units must be moles per liter. We can't do moles per milliliter or anything else. It has to be moles per liter. Remember also that a mole is a number. We are counting the number of particles. So if you see, for example, a half mole, that's kind of the same as saying a half dozen. We know that a dozen is 12, so a half dozen is 6. Well, 1 mole is 6 with 23 zeros after it, which is really big. So half a mole is 3 with 23 zeros after it. So there's an example here, 6 moles of, remember this is solute, in 2 liters of solution. Well, we always divide that out to make it 1 liter on the bottom, so 6 divided by 2 is a 3 molar mixture. So go ahead and pause here and write down molarity. Now this slide is slide number 4, and it's going to be really important for you when you go to solve concentration problems. It's really going to be like your cheat sheet for the 3 representations that I talked about on the previous slide. So the first representation that we talked about was percent. So percentages. In blue here, that's the equation. Solute divided by solution equals the percentage. Some problems are going to give you the total solution and the percentage. So for example, in a 500 gram solution, that's 50% solute. How many grams are solute? So 50% of 500 grams is 250 grams of solute. Other problems are going to give you the amount of solutes in solution and ask you to find the percentage. So either way, this equation, you might have to rearrange it, but that's the equation you use for any percentage problem ever. Now, important side note, if you see m over m or v over v, that simply means that you have to use mass over mass or volume over volume. And it's telling you which one. So you'll see problems that say percent m over m, that's telling you that you're working in mass. Or percent v over v is telling you that you're working in volume. The second mathematical way we had was ppm, or parts per million. Again, that's going to be solute divided by the total solution equals parts per million. So it's really similar to percent, but instead of giving units in grams or in milliliters like mass or volume, you'll be given units in parts. Typically, these problems will tell you that if you have 3 parts in 500 million, it'll ask you to convert to a million parts. These problems are usually pretty simple. The last mathematical representation was molarity, and remember that with moles we are literally counting the number of particles we have in a liter of solvent. And so here's your equation for molarity. It's moles divided by liters equals molarity. And so even if they give you some weird liter amount like 0.76, for example, hint, hint, that's on the first problem, you can still set up the division. So for that first problem, it gives you half a mole, 0.5 moles, and it gives you 0.76 liters. You set it up just like this, moles divided by liter, put it in your calculator and hit enter, and that will give you the molarity. Remember that for molarity, we need to use an uppercase M. So when you attack these concentration problems, what you should do is decide which type of problem is it. Is it a percentage problem, is it a ppm problem, or is it a molarity problem, and then use the appropriate equation, and I've written all of those in blue. Now, there is one last thing we can do with solutions. So if we were going to say that we had 3 problem types before, this would be a 4th problem type. And that is making a dilution, where we change the concentration of a solution. And typically, we are not making a solution more concentrated, we're making it more dilute. And we do this in chemistry and medicine all the time. And here is the equation right here. It'll also be on the next slide. So all you need to write down right now is how to make a dilution. So go ahead and pause here and get that down. All right, here's that equation again. It's right here. This is the same one. And what it is the molarity from the original solution, which is the more concentrated one, times the volume of the original solution, the more concentrated one, is equal to the molarity of the second one times the volume of the second one. And remember that the second part is the more dilute solution. So these are molarity, which we can calculate using the third equation from the 2 slides ago, not the number of moles. The total number of the moles is the same. So here's what I want you to write down on the slide. I want you to write down this equation, and I also want you to write down that the total number of moles of the solute is the same. We added more solvent. So go ahead and pause here to write that down. The other thing that you should write down from the slide is that M2 and V2 are of the more diluted solution. So that will help you when you're reading the problem, is that M1 and V1 are from the more concentrated solution and M2 and V2 are from the more dilute solution. So go ahead and pause and add that to your notes too. So we're going to do an example dilution problem to help you look at how to read these problems, because that can be really important. So this problem says how many milliliters of aqueous 2 molar MgSO4 is magnesium sulfate solution, must be diluted with water to prepare 100 mils of aqueous 0.4 molar magnesium sulfate. So when we look at this, the very first thing I see is how many milliliters. Milliliters is a volume, and that's of the original solution, the concentrated one. So that's telling me right now that I don't know what V1 is. I also see here's a molarity, and this is my M1 because that's the more concentrated one. This one is less concentrated, it's a smaller number, so this is M2. And I need 100 mils of this less concentrated one, so this must be volume 2. Now, before I go a whole lot farther with this and how we read this, let me remind you of your dear best friend from the very beginning of the year, which is guess check. So here we are with our dear old friend guess check. G is for givens. U is for unknowns, that's what we're looking for. The equation is how we relate all of those things, and then once you have all of those pieces, you substitute, you solve, and you check your answer. So you'll notice on the previous slide that I underlined the givens in blue, and I wrote the unknown in red. That's my own personal color coding. You don't need to color code. I like to do it. And remember that our equation in this case is the dilution equation. You have 4 potential equations that you can use in concentration problems: percentage, ppm, molarity, or dilution. So make sure you check which problem you're using which problem you're solving so that you know which equation to use. Pearson also, the textbook where this PowerPoint comes from, also sets up their problems in a similar fashion. They call them knowns instead of givens, but we call them givens. And they list exactly the same information that I pulled out of the first problems, and then their unknown is over here. And that was V1. The other thing that they list down here is the equation. So now that you have all of these numbers, you can go ahead and plug them in and solve the equation. Solving the problem would look like this. If V1 here was our unknown, we get it by itself by dividing both sides by M1. We plug in all of our givens to the equation, and we get our answer, which in this case is 20 mils. And that's how much of the original concentrated solution we have. When we go to check our answer, in this case, since we were looking for a volume, we'll compare the volumes. The second volume, the dilute volume, was the 100 mils. So the original concentrated volume needs to be smaller than that since it's concentrated. 20 is in fact smaller than 100, so I'm feeling pretty good about this answer. So that's all that I have for you about concentrations. I'll summarize really quickly and say that you had 4 ways to solve concentration problems. Depending on how we represent them, we either use the percentage equation, parts per million, or the molarity equation. Or if we're doing a dilution problem, we use the dilution equation. So make sure that when you're setting up a problem, you check to make sure that you're using the right equation. Of course, if you need to, this video is available for you to rewatch, and the notes without the video are on Schoology in the Unit 5 folder. So good luck on solving your concentration problems.